Welcome to CS270 and the beginning of the online section of our class. So I'll talk this week about virtual memory and also maybe a little bit about cache. But starting with virtual memory, I guess one of the big questions is what is it? So that's what I'm hoping to address today, and maybe we'll see a few of the reasons you might want virtual memory, and then we'll get into more details about the reasons you might use virtual memory and how it can be helpful for an operating system like Linux in later videos. So in old computer systems, so this would have been large computer systems in the 70s or so, and things like PCs in the early 80s, maybe even up to the late 80s, and embedded systems, smaller computers or microcontrollers, things like the Arduino, but also things like video game systems up until even the late 90s, use something called physical addressing. That is, there's some amount of main memory, so that's shown in the right over here, and let's say 64 kilobytes of main memory to fit a computer system from the early 80s. So 64 kilobytes of main memory means the addresses you can have go from 0 to 6,535. M minus 1 here is the amount of memory minus 1 because we start from 0. So in a computer using physical addressing, when a program running on the CPU refers to a particular address, let's say address 4, then that refers to that particular slot in main memory. There are a few obvious difficulties with this. I can't have two different programs both referring to the same slot of physical memory, or if I do, it means they're sharing that physical memory and need to coordinate. So, to support multi-user systems in the late 70s or so, they developed something called virtual memory. And I should say that elements of virtual memory were present even earlier than the late 70s, but the late 70s is when it began to become popular in computers like the VAX, for example. So in virtual addressing, we still have some amount of main memory. As time has gone on, the main memory on modern computers is, of course, larger than 64 kilobytes. So maybe let's say 8 gigabytes. And the addresses of main memory, that is the physical addresses, go from 0 up to 8 billion minus 1 or something along those lines. When a program, though, refers to a particular address, for example, 4100 here, then rather than that being the 4100th slot in main memory somewhere down here, instead there's a piece of hardware called the Memory Management Unit, or MMU. That piece of hardware uses some tables that are themselves stored in main memory to map that address, 4100, into a particular location of physical memory. So address 4 in this case. And the nice thing about this is simply by changing the tables that are in the MMU or that the MMU refers to, we can have another program or another part of the same program use the same virtual address and be referring to a different physical address. That gives us a lot of benefits, which we'll get into in more detail in some of the later videos. So just for a little bit of terminology, a virtual address space is the kinds of addresses that a program might use. What something running on the CPU sees. Each different program might have its own virtual address space, and that address space has some size. So, for example, on a 32-bit system, the size of the virtual address space might be 2 to the 32 bits, or about 4 gigabytes. On a system like an AMD 64 x86 64 system, the virtual machines we're using, this virtual address space has 20 or 48 bits. So it goes from 0 up to 2 to the 48th power. 0, 0, 0, 0, followed by 12 Fs. We also have the physical address space. This is the memory that the hardware sees This is the actual RAM in the system. On most systems, that's a power of 2. Doesn't necessarily need to be. So for example, on my home computer, that's something like 16 gigabytes of RAM. So I have physical address slots or physical addresses going from 0 up to about 16 billion minus 1. Whereas the virtual address space on that system is much, much larger. So why would we use virtual memory anyway? Well, we have a few different reasons. For one, it lets us use main memory more efficiently. Rather than having to have the full address space represented in main memory, and things that are in RAM are the things that a program can refer to directly, we can use RAM as kind of a cache for a much larger virtual address space. This means that programs can open large files or memory map large files, as we'll see in a later video, but only the parts that are actually used have to get loaded from disk into memory. Also, it means that if I've recently used a file, its contents are already stored in main memory. That had to happen for us to be able to read it in a program. And if I refer to that same file again, even in a different program, possibly even a program belonging to a different user, I can still refer to that same thing in memory without having to load the file for disk again. So it lets us use our RAM as a cache for access to the disk. It also simplifies memory management. Each process running on the system gets the same address space. So we don't have to worry when we're compiling, or rather when we're linking a program, about what address it needs to be loaded at runtime. We don't have to worry about whether other programs might already be using that same address. We can instead just decide what that address is going to be, and with the help of the hardware and the operating system, make sure that when this program is running, it sees the layout of memory that it expects in its virtual address space. And different processes, different programs running, or different copies of the same program can see the same view of the address space, even though they have different variables and are really using different physical memory. They don't necessarily share anything, or they share a limited set of things. It also lets us isolate address spaces as a form of security and as a form of bug prevention. If a program has a problem that causes it to dereference a dangling pointer or to overflow a buffer, at the very worst, it can only mess with its own memory, with the memory that's been allocated to its virtual address space. The other programs running, even ones belonging to the same user, are isolated from it. They have different mappings to main memory. And for the parts that are shared, or for the parts that are used by different programs, we can make sure that they're read-only, so that even if I can accidentally read from it, I can't accidentally write from it. This also lets us have programs running on behalf of different users, all loaded into memory at the same time, without having to worry about the security implications, usually. Meaning when one program is trying to access memory, there is no way it can get to the memory belonging to other users, and no way it can get to the memory belonging to the core of the operating system itself, the kernel. So we'll see more about these different reasons for virtual memory and how we can make efficient use of virtual memory in later videos. Thanks for watching.